last lecture of today. Let me just reiterate, afterwards we have this get together, okay? So don't run off to your hotel. Please.
So, in the typeface, I want to give a short introduction to what is called curvature-free geometry or systolic geometry. And of course, there are maybe several different types of curvature-free geometry, for example, Cauchy geometry. So maybe I will say about the relationship of this at the end. So I will start by a bibliography and by what I plan to cover. So my talk is in a way an introduction to Riemannian talk, because we have some overlap. And my plan for the lectures is first prove the systolic inequality. So it will be later clearer what I mean. Inequality of Gromov. Systolic inequality for surfaces. To Gromov systolic inequality for aspherical manifolds. So this is theorem 1, theorem 2. So I plan to do this in detail. So with no prerequisites, so to speak, and then if there is more time, the relations to cos geometry or other topics. If I find out that using this makes me go fast, maybe there will be 3. Okay, so I have here a short bibliography which covers what I'm going to talk about, in fact a bit more. And so what is curvature-free geometry? Well, we try to give geometric properties of Riemannian manifolds, but without any curvature assumptions. So usually we put some curvature assumptions, but here we try to say something interesting geometrically that works for all manifolds. So one can say that this started with Poincaré, whether every closed Riemannian manifold has a closed geodesic. So there is always something like that. And well, this is easy, I would say, M is not simply connected. And it's more tricky if it is simply connected, so in particular for S2. So Birkhoff had this brilliant shortening idea. And in fact, Lustening et Fett later on showed that this technique works more generally if just assuming non-trivial homology on the manifold. So we know this is true, but then this is more, in a way, not very geometric. So an interesting geometric question is whether one can bound the length of the shortest closed geodesic. And now bound, what does it mean bound? Well, the only thing we have is the volume of the manifold, right? So we'd like to bound the length of the shortest closed geodesic by the volume of the manifold. Then one remark is, of course, we are not talking about a lower bound. So even, okay, so let me rephrase it. So fixed, maybe I will repeat myself, but fixed volume, so equals 1. Well, let's take this manifold. Well, of course, if I fix the volume, I can pinch this and make a geodesic very short, right? So I can make a torus like that. So certainly there is no lower bound, right? You can get as small as you like, but if you think about it, you cannot get as big as you like, right? So there is an upper bound. Okay, so there are so no lower bound. Upper bound, and the upper bound is the result of Loewner that I'm going to say soon. So Loewner's result was known, and then at some point several people apparently proved the generalization to surfaces with many holes. But the result was quite weak. I mean, it was obvious that if you have more holes, this thing has to go down, but the bound has to get smaller, but it didn't. And Berger was apparently, so there are a couple of anecdotes associated to this problem. So in the 60s, Berger met Tom in a library and told him about this, and he says that Tom said, c'est fondamental. It's an important question. So I was first surprised that some great geometer like Berger, well, he was young then, but still needed a confirmation by Tom about this question. It seemed obviously an interesting question, but so that's maybe the moral of the story, that it's good to talk to other people. I don't know if Berger was just polite. The fact is, Tom, I mean, was just polite to Berger, but Berger really got encouraged and popularized and wrote papers about this question and made it widely known. And in fact, even later attributed the question to Tom, even though this, I mean, Tom never wrote anything about it as far as I know. Well, the other two interesting facts is that Berger stated the right questions, and maybe he was very much in the curvature frame of mind. He says himself he didn't manage to solve the problems. It was later Gromov who solved them. And there is a second anecdote associated to Gromov. Gromov said, oh, I thought immediately that this is a simple problem that one can solve using the co-area inequality. And I started, but then I got stuck, and then he came out with a brilliant but complicated proof using isoperimetric inequalities that had a great influence, and a lot of research was done just on the methods even, and the methods were very important, but it turns out actually that Gromov was right, and 30 years later, there was a simple proof just using co-area inequality, and I'm going to present you that. So it's a happy instance where mathematics gets simpler. Anyway, so that's my anecdotes on the topic. So let's go back to Berger's question. So Berger's question is not trivial even when the fundamental group is not trivial, right? Because we know that there is a geodesic, but we have no a priori bound. And now the definition, so the systole, so we call the length of this shortest non-contractible loop the systole of the manifold. So the question is if we can bound the systole by the volume, right? And I'm going to state the results in dimension 2. So I will start now by explaining the result about surfaces. So Loewner, in 49, he gave this bound for the systole of the torus. And now you see there is, I said, bound by the area, by the volume. You see I have this square root, but the reason is simple. Well, one way is to just forget about it. If you don't like the square root, just forget about it and take area to be 1, right? And that's not there. You can agree that you will always care about manifolds of volume 1, and then this disappears. But the reason I have the square root is, of course, if you have a metric, well, I'm going to denote the metric by mu. If you have a metric mu, and you change to lambda times mu, then this gets multiplied by lambda, right? But this, the area, gets multiplied by lambda squared. The only way to relate these two things is to relate one with the square root of the other, right? Because one gets quadratic, so that's why we have these squares, and then later. Okay. So as I said before, there were some early results about general surfaces, but the point is you expect as the genus increases, as the Betty number increases, this bound to get better and better, right? And this is what Gromov proved. So you see as g goes to infinity, this, so let's remark what is the point of this is that this goes to 0 as g goes to infinity, right? So we have a better bound as g goes to infinity, and now it turns out that this is optimal. Okay, so this is optimal. Oops.
Can I ask a question?
Yes.
So is SG orientable or no?
Okay, actually, it doesn't matter. I mean, I will take it close to orientable, thank you, but it doesn't matter much because if you take the double cover, it is orientable and the systole is not going to change much and the area is not going to change much. So, but I like orientable surface, so I will take it to be close to orientable always. Okay, any other question? Okay, so this is the object we are trying to study, and now this picture, maybe I should acknowledge, is done by ChatGPT. I wouldn't be able to draw this. And actually, it also told me that this has genus 20. I said to draw a surface of genus 20, and that's what it came up with. So either it doesn't know how to count, or it knows that 20 just means big, and you don't count. Right? So I don't know what it is. If it's the second, I'm more impressed. 20, that's not 20. Even me, I can say it's not 20. But this is, okay, so, I mean, usually we draw pictures of surface often. We draw pictures of surfaces in a boring way somehow. So ChatGPT did something better, so we draw it something like that, right? But this is not what the surface looks like. This is what the surface looks like, and it turns out we have really no clue metrically what the surface looks like. I mean, there are many problems we don't really know much. I mean, I'm going to talk about a bit about it later, but anyway, this is my object, and I want to find a bound for the systole, and I drew a couple of systole, well, candidates for the systole here, this blue and this red here. Well, maybe there are smaller. Okay, so I'm going to start with something easier. Actually, I'm going to start with the systole of metric graph. So what do I mean by metric graph? Well, I mean a graph except the edges not have necessarily the same length. Maybe this is 0.3, this is 2.7, and so on. Okay, so this is a metric graph. And as we said, well, we have to decide what the total length is b, or we have to normalize, right? So because when we rescale the metric, the systole changes, right? So in fact, we're interested in a quotient, systole over length. In the literature, actually, it's always the other way around. I'm not sure why, but this seemed more natural to me. So we want to find an upper bound for fixed b. And now we can normalize and take, so b is the first Betti number, right? So here. So, and we can define the systole the same way, right? The smallest simple closed curve in the graph. And now you see naively how one would go about it. Well, if we have this graph, which has length 1, right, we can normalize and take length 1, the systole has length 1, and now the obvious graph of length b is this, right? Why does this? So I can take b circles, or if you want it to be connected, I can do it like that, and then if this were the best one, the systole, of course, would still be 1, right? So, yeah.
So what is the Betti number?
Oh, take, I don't know what is the best way to, I mean, you can use the homology, or if you know what is the fundamental group, you just Abelianize it, right? Take the fundamental group and Abelianize, or you take the homology of the graph, right? Which is going to be z to the n, and this n is the first Betti number. Or
it's a graph, it's a free group. Can you just...
Right, yeah, it's a free group, so it's just the number of generators, if you like. I don't know whether. So the fundamental group is a free group, and the first Betti number is the number of generators of this free group. So, or, okay, actually, I'm going to give a different definition because I promised I will be elementary. So I will define the first Betti number in the following way. I have my graph. I'm going to take a maximal 3 inside, okay? And then the number of edges that are not in the maximal 3 is, the cardinality of this is the first Betti number, is b. Okay? The number of holes in the graph, in a way, okay?
That makes sense.
So I take a maximal 3 and then I count how many edges I have outside, and this is b. Okay, this is my b. Okay. Well, and yeah, if I take a non-connected graph, it's just the number of poles and it's B. So yeah, so if I normalized and I instead took the length to be 1 as I did before, of course you would see, it seems in the obvious examples that the length drops very much. It becomes 1 over B, right? But that's not what happens in fact. So we cannot have this, but still the length is going to be the systole is going to be much smaller than B, right? It's going to be of the order of logarithm. There is a constant. I'm not going to go anywhere close to the best constant. What I'm going to do is, I don't really care much about this constant, so I'm going to prove it for phi, right? So it's a constant I'm going to give it explicitly, and yes?
So when you say supremum of systole gamma over length of gamma, so
for fixed B.
So are we taking supremum
over all graphs? All graphs gamma with P1 gamma equals B. Okay, so I fix, so to speak, well, kind of the topological type, and I see. So it's like before with surfaces. I mean, when we take the systole, we want this to work for every Riemannian metric, right? So now we want it to work for every metric on the graph, but we fix the topology of the graph. Okay, now I want to see what happens as the topology gets more complicated. So as the topology gets more complicated, I expect the systole to get comparatively smaller, right? So the length is B, and then the systole is much smaller than B, it's logarithm B. Or if we, okay, so let's forget our normalization. So if I forget my normalization length is equal B, and I have the length to be L, so length, so let's change this and make this L, right? Then the systole, so I rescale, and I have the length to be just anything. Then the systole of gamma prime is going to be L over B times the systole of gamma, right? But this is less or equal than 5, as I said, logarithm B, length of gamma prime over B. Okay, so I can rewrite the same formula without any assumption on the length, right? So this is equivalent. The systole of gamma is less than this. And again, the point is that as the topology gets more complicated, I get a smaller systole. So this tends to 0 as B goes to infinity. Right? That's the point of this theorem. Okay, and now it turns out that this is again optimal. There was an old result by Erdos and Sachs that said that there are graphs of degree 3 such that Bn goes to infinity and the systole is greater than this, right? So we get the other inequality. So yeah, the systole is not smaller, much. It's not 1, it's not constant as in my example. So these graphs are constructed by probabilistic methods, and later there are more examples using expanders and so on. But they are not graphs that I could draw, right? It's more of an existence by probabilistic methods. Okay. Okay, let's go back to the proof. In the case of graphs, so I have a finite graph and I have the number VEn, the number of vertices, edges, and connected components. So my result will also work for, the result also works if you have more connected components. In fact, as you saw in my previous example, if you have more connected components, it's kind of easier, right? Okay, so first the handshake lemma that says that the sum of the degrees is equal to 2 times the number of edges. Well, this is kind of obvious, right? Because you see when you count degrees, you count each edge twice. 1 for this and 1 for this. That's why we have the sum of the degrees is equal to 2e. And in particular, if gamma is trivalent, so that means at least trivalent, that means we have at least 3 edges going out from every vertex, then this sum is less than, greater or equal than 3v, so we have 2e is greater or equal than to 3b, than 3b. And now the Betti number, well, you can use what I said before about trees in the definition to prove this, that if the graph is connected, this is E1 minus E minus V plus 1. Because you see, if you take a maximal tree, it has E, how many? Okay, so we have E edges, and now the maximal tree has exactly V minus 1 edges, right? So max 3, so let's prove that, max 3 has V minus 1 edges, right? So what is left out is E minus V minus 1, which is E minus V plus 1. Okay? So we have this, B is equal to E minus, and of course if we have many connected components, we just sum up all this and we get this N. Right? Okay, so if gamma is connected, B is equal to E minus V plus 1. Right, so, and this is greater or equal to E over 3, so I use here this inequality, right? V is less or equal, so what I use here is that V is less or equal to 2/3 V, to 2/3 E, sorry. So I get this inequality. So E, so I'm generous with my inequalities, I could have a minus 1 there, but E is less than 3B. So my point is that B and D are comparable, right? So the number of edges and the Betti number is comparable. And here I assume, well, in general they're comparable because my graphs are going to be trivalent, right? At least trivalent. Okay, so yeah, we get that T. Yeah, as I said, E is bounded by the Betti number, and now for the purpose of the systole, okay, maybe what I said was not quite correct. For the purpose of the systole, of course, these graphs are not good graphs. Right? They're not going to maximize the systole. You can just take out this part. Okay. So that's why we have also the other inequality. So the number of edges is basically up to a constant, the Betti number. Okay, so let's try to prove our theorem. So maybe the theorem, go back, it was this one, right? So I'm trying to prove this now. And I'm going to do it first in the easier case where I have edge length 1. Oh, I should have said, okay, I cited Bolobas, but the study of systole of graphs started earlier on by Todd, right? So in the 40s. Graph theorists studied systoles, but I think maybe Bolobas and thought about the case where the edge lengths are not necessarily equal to 1. Okay, so in the classical case, okay, again, why I'm doing trivalent? I said that I'm doing trivalent because, first of all, edges of degree 2 don't matter, right? So when I'm thinking about geometric graphs, this picture, I'm just replacing it with this picture. I just erase this vertex because it does nothing. And also, I don't care about things like that because they don't contribute to systole, right? So this is kind of stupid. It increases the length but doesn't increase the systole. So certainly, I'm not interested in graphs, in edges of, in vertices of degree 1. Okay, so I know that my graph, the graph that realizes the systole, is going to have degree greater or equal to 3 for each vertex. Okay, so let's start with the case where the degree is exactly 3 and the edge lengths are equal to 1. Well, what happens then if R is less than the systole? Well, I have a lot of length. I get a lot of length. So because my graph is trivalent, so I have 3 edges going out, and then since I'm smaller than the systole, I have more edges going out, right? They cannot go back up and so on. And now, after R steps, you just count how many you have, and you have that many, right? So the length is quite big, right? So in particular, if this is greater than the length, then R is greater than the systole, right? So then R, maybe I'll write it, then R is greater or equal than the systole of gamma, which basically gives us the inequality we want, because when I have equality, so if I have 3 times to the R minus 1 equals length of gamma, I get R2 to the R minus 1 equals length of gamma over 3 plus 1, and I get that R becomes logarithmic in the length, which is what I was promising, logarithmic on the number. Okay, so maybe I'll write it now. So then, okay, I took this plus 1 there, first of all, because I don't care about constants and I'm generous, and then because R is supposed to be an integer. So, and now here I use star, the inequality I proved earlier, to replace this by B, right? Because remember, we had this relationship, E is less or equal than 3B, okay? So I got, in this case, that the systole is less than 2 times logarithm B, okay? So again, the idea was, okay, if the systole is big, I get a lot of length. I get exponential length, right? Because I have this tree that branches and gives me exponential length. So the systole is logarithmic on the length. Okay, that's all. That's all. And these are the precise inequalities, but if you don't like algebra, just think, well, if the systole is R, you get exponential length, right? That's all I'm saying. Okay, what if the lengths are less than 1 rather than 1? Again, equivalent. Well, then the length gets even bigger, right? Because your graph branches even more. Okay, so if you like, you can fold the ball of your graph into the ball. So if you have more branching, say you have something like that, branch like that, you can just fold so that you branch at the point 1, right? But this decreases the length, so the length is even bigger. So the systole, the same inequality applies for the systole. Okay, now we may assume that gamma, yeah?
Can you explain more how this decreases?
Oh.
Instead of the length,
Yeah, okay, let me. So, what I'm saying, I mean, maybe I'll say it first heuristically again, and then I will try to prove it. What I'm saying is, if the lengths are less, the edge lengths are less than 1, well, I go here. So before I branched after distance 1, but here I branch after distance 1/2, right? Okay. So what I'm going to do is I'm going to define a map from this to this that is length decreasing. So how do I do it? Well, I just fold till I get to the length 1. Okay, so just fold. So there is okay. So let's call this 3T1 and let's call this 3T2. So here edge length is equal to 1, and here it's less or equal to 1, right? And I pick a base point, I map it to the base point, and then I pick a direction here and the direction there. And now maybe my direction branches before 1, so it branches like that, okay? Well, then I map both these edges, so I go up to the length 1, and I map this part, maybe this part, I map it here, okay? And then I continue, right? Then I branch. So these two just branch, right? Go there. And then I keep doing that, right? So this this map decreases length, right? So this tells me that T1, I mean, if I take a ball of radius r in T1, is bigger than a ball of radius r in T2, right? Which is all I need for my inequality to work. Okay? So, yeah, we have more branching basically, so we have more area, so the systole again satisfies the same inequality. Okay, and now, I say we may assume that gamma is trivalent connected. Why? Well, as I said, one terminal edges are stupid to have, right? Because they add length and they make nothing to the systole, so certainly this doesn't exist. And certainly this makes no sense because I can erase this vertex and just consider this as a single edge. Okay, so the only question is, what happens if I have bigger degree, like that? Well, then what I do is I just split this. I add a very small edge, epsilon, and since I'm taking supreme and so on, this doesn't matter because I will make it get smaller and smaller, and then the supreme will be the same for trivalent graphs and for the other graphs. Okay? So I just replace vertices by very small trees, and you can make it trivalent, and you make negligible effect on the systole and negligible effect on the length. Okay? So that's all. Yeah. So I will use this kind of trick later also with surface. I mean, if we change things just a bit on the metric, this has no effect on the systole and no effect on the area. And since we are working with Suprema, we are allowed to do things like that, right? If you think about it, they have no effect. Okay. So I can assume that my graph is trivalent connected. And now I have already proven it if all edges have length less or equal to 1. That's fine. So I can try to see, now I'm going to use induction. So this is a new idea of this proof. Okay, before I did it in one stroke, but now we'll just simply use induction, and I only care for big B, right, for big graphs, because my result is asymptotic, so I will start my induction at 5. Well, arbitrarily, it doesn't really matter, and I'm going to say, okay, the systole is less than 5, and log 5 is more than 1, good, so that's less than 5 log 5. So it works for small graphs, and in fact it works, yeah, for smaller graphs. And now let's take an edge that has length greater than 1, and let's consider the graph where we take out this edge. Okay, so I have some edge, right, f that is big, and I take it out. Well, two things can happen. Either the graph stays connected, or this edge is going to disconnect my graph. Okay, so I'm going to consider these two cases separately. So if gamma 1 is connected after I take out this edge, then B1, well, since the graph stayed connected, I can find still a maximal tree there, right? And I have one less edge outside the maximal tree, so the Betty number dropped by 1, and the length dropped by more than 1. Okay? The Betty number dropped by 1, and the length dropped by more than 1 because my edge was longer than 1. So I have Betty number less than 1, and the length dropped even more. Oh, but then by the inductive hypothesis, the systole of this smaller graph is smaller than this, right? If B is bigger than 6 now. So, and this is less than 5 log B, and I'm done, right? So just by induction. So gamma 1 is fine. So I do induction on B, right? And if gamma 1 is not connected, then I get two graphs, and gamma 2, gamma 3 are connected. And now the lengths of this, well, the sum of the length before it was B, now is less than B minus 1. And the sum of the Betty numbers is B, of course, because this was on the maximal tree. The length of gamma I, right, since we have this, the length of some gamma I is less than B1 of gamma I. Okay, but then I can apply my induction hypothesis on, say, the smaller one, and I'm done again, right? The systole of gamma I is less than this, is less than 5 log B. So the proof is kind of simple by induction, but surprisingly it gets the optimal result, okay? I mean asymptotically optimal result. Okay, so yeah, I'm not sure. Somehow this is not really done in these geometric papers that treat the systole. They assume it, and I haven't read the graph theoretic literature. I don't know if there was somebody earlier that did something similar, but I guess in graph theory, usually they didn't consider metric graphs. That's why it came late. Okay, and now let's see how we can use that. So the reason I did it is because that was not Gromov's original proof, but Kodani used graphs to bound the systole for high genus surfaces, and Saburo later refined this method too. So we are looking for this for a bound of systole over, as I said, square root area, because as I said before, when you multiply the metric by lambda, the systole multiplies by lambda, but the area by lambda square. And again, I can normalize and say, okay, since G, now G is the number of holes, the genus, right? So this is genus equals to 3. And now we have a similar theorem as before. The systole is less than 10, well, some constant, 10 logarithm G for big G. So I'm not going to bother about small surfaces. And equivalently, I can do the same calculation as before. Let's see if I manage. So if you don't like this, and you want to take area of sigma prime to be just A, say, right? Then the systole of sigma prime. Then you have to multiply the metric by square root A times square root G, right? So to get the systole of sigma, and then if you replace this, you get 10 log G square root A over square root G. Okay. So I can write this in general. I can write this without this normalization. And Katsaburo showed that in fact you can replace 10 by pi for big G, but we don't really know the fine result for this, unlike the case of genus of torus. We don't have the best constant in these inequalities. Okay, so now I will start. So I plan to go through Kodani's proof, and as I said, I will give an elementary exposition of this, but I'll still need some background, which is, well, which is, so to speak, classical. And if you are not familiar with this, I hope you will agree that it's kind of geometric and topological common sense, right? So I'm going to state these theorems, but I think if you think a bit, you should be able to believe these things are true. So I'll need some differential topologies. So both for this theorem, some of this I will only need for later, for the later theorem in dimension n. So I'm going to state the background for both of the results. So such theorem, so if we have a smooth function, then the level sets most of the time are smooth submanifolds, right? So this is classic, and now if I have a Lipschitz map, then I can approximate it, so I can get another map that is very close, but so that the level sets are smooth submanifolds, and if the manifold is closed, in fact, I can even assume that this is a Morse function. There are only finitely many places where I get critical points. Again, why we're interested in this is similar to the situation with graphs, where I change the degree, right? So we allow ourselves to make small changes to the metric or to our functions because they have small effect on volume and systole. So this is something that I will be using, and maybe I won't even be stating it. I will assume that things are nice. And now, well, I'm talking about area and so on, and volume. So now I'm going to define them, and we can simply take it to be the Hausdorff measure. So the Hausdorff measure is a bit of, if you haven't seen it before, it's a bit scary, this definition. You take cover and then you take a limit, and delta goes to 0. So I'll leave it a bit to read. So we take as a limit. Well, the good thing about it is that unlike Riemannian volume that takes some background to define, right? You have to know volume forms or whatever. This, you only need a metric. As long as you have a metric, you have this measure, okay? So it's more general. It is a measure, and of course, if I have a Riemannian manifold, you could take that to be the definition of the volume, right? So the Riemannian volume, it turns out, is equal to this. So this is what I will take to be the Riemannian volume. So when I say the n-dimensional unit ball, I mean, of course, in Rn, right? In standard Euclidean space. So the Hausdorff measure is basically the volume up to a constant. And I will also need the co-area inequality. So maybe I'll do a picture. So what does the co-area inequality tells me? It tells me if I have a region and I kind of foliate it, okay, using a one Lipschitz function, then the volume is just the integral. So this is another way to visualize the Hausdorff measure. The volume is just the integral of the volumes of the slices, right? So that's all. So the co-area inequality is just the geometric version of Fubini theorem, okay? So I'm going to state it more precisely, but it's basically Fubini theorem, except you do it geometrically and carefully. So if we have a Lipschitz function on a manifold, and we have a nice subset where we can define volume. So now here, the fact that I have one Lipschitz and not an isometry or something like that gives me that I get an inequality because things could collapse, right? Okay, but what I will generally be using this for the distance function, and what it tells me is that the volume is bounded below by the integral of the volumes of the slices, okay? So for the experts, of course, all this is given, but maybe not everybody familiar with this. So this is all co-area inequality says, right? And if you integrate this, you get a lower bound for the volume. Oh, and finally, I will also need, actually this is for my second talk, I would also need to pass from manifolds to Riemannian polyhedra. So I will have something like a simplicial complex, and each simplicial complex will be given a Riemannian metric, and when I have adjacent simplices, the metrics agree on the boundaries, right? So this is a Riemannian polyhedron, and all the previous results I can use also for Riemannian polyhedra because I can do it face by face, all the things I said before. Okay. So now I can give you an outline of Kodani's proof. So first, we want to slice the surface into thin slices, so say of width 1. And now each slice we want to kind of approximate by a graph. And now the second step is ensure that the pi1 of the graphs injects, so the systole is smaller than the systole of the graphs, right? So we just cut and then we want to bound the length of the gamma i's using the co-area inequality. So because if the gamma i's are too big, then the co-area inequality will give us too big volume. And now use my previous theorem for the systolic bounds for graphs. Well, we are going to have a bound on the lengths and the bound, and we'll have also, we'll also see, okay, that's another part, that the graphs gamma I are complicated, right? So I will cross, this is part of Kodani's trick to ensure that they are topologically complicated, and then the systolic bound for graphs will give us a result. Maybe before doing the actual proof, I want to show, I want to show some examples. So what can happen, right? So, well, first of all, what happens if you draw your surface the stupid way we do it when we teach topology, like that, right? So it's like that. Okay, we said that, so my graphs are not going to be complicated in this case. right? So if we draw the surface like that, and we take, okay, so what I'm going to do is I'm going to fix a point and take the levels of the distance function, right, here. Okay, remember, I said the area of my surface is G, and G is also the number of holes, right? And now if these are distance 1, right, somehow naively, if you say, okay, this is distance 1, well, by the co-area inequality, well, some level here is going to have actually length 1, so it's going to be even much smaller than what I want. I want to prove that this is log G, right? But this is going to be less than 1, right? And this is going to be non-trivial. I mean, it's going to be a systole. Okay, so if my surface is simply looking like that, then it's easy, right? So the whole difficulty is that my surface can have a strange shape. Now, on the other hand, if we are on the other extreme and my surface, you know, is very, I don't know how to draw it, has a lot of holes here, then I'm going to get a complicated graph. And this is how it will be done, right? So the difficulty is when the diameter of the surface is small, so to speak. When the diameter of the surface is big, you get it for free. Okay? So the difficulty is basically imagine how a general surface of genus G looks like. So what ChatGPT did earlier. Okay. So let's start. Oops. Let's. Okay. Okay, so let's start this. So probably I'll finish the details of the proof. I don't know if I will do the whole proof now, but I will start. So we have a closed orientable surface of genus G. We normalize the area is G. And now I'm going to take, well, I said I'm going to take a base point. So why not? I'm going to take a base point to lie on the shortest non-contractible loop. So the systole, something that has the length equal to the systole, and I'm going to look at the level set of this distance function. And we may assume again by, okay, the original thing might not do it, but if I change slightly the metric or the function, we are going to have a Morse function. So all of these level sets are going to be just unions of finite simple closed curves, right? And at the finitely many points, I'm going to have a critical points of index 0, 1, or 2. So what does it mean? Actually, index 0 will be when a point blows up and become a simple closed curve, and this will happen only at the beginning, actually. I'm going to have only one point like that. When I start at the point P, right, I will get this, but I will never get it again, right? So this will happen only once. And now, index 2 is when I have a simple closed curve that becomes a point, right? So I add a disk there. And one actually there are two types. Maybe I will write the second. Oops, that was at the wrong point. Okay, so type 0, as I said before, a point becomes simple closed curve. Type 2, a simple closed curve contracts the point. And type 1, well, there are two possibilities. Either a simple closed curve will split into two. So I'm going to have this, and then this will become like that, and then it will become 2. So this is type 1. Or I will have two simple closed curves, and then they're going to collide at the critical point, and then they will become 1. So this is type 2. Okay, now let's see what happens geometrically in each one of them. Well, this one just kind of adds a handle there. I mean, not exactly a handle, but this is what it does. And type 1, yeah, we have something like that. So type 1, there is a hole, right? We had one hole and now we have two holes in my surface. Okay, and now since we have genus G, we have this equality, right? So again, these N1 points, they drill holes, and type 2 add handles, right? And eventually, the number of holes has to be capped off, right? So, and it's going to be capped off either by this, so every time we do this, 2 holes become 1 hole, right? So the holes, so this increases the holes, this decreases the holes, and this caps off the holes, right? And this has to be end 1 is because when we start we create holes, so we create a simple closed curve. And N2 is going to be G because I have G hand. So this I'm going to leave as an exercise if you want to think about. But I'm going to assume this, that N2 is equal to G and I'm going to use it. Okay. So this is the part. Okay, well, I have a bit time, but I'm not sure I will be able to get to the end. Are there any questions? Yeah?
Just could you show the picture actually? Or did you delete the picture where you either add holes or?
Right, yeah,
What's
okay.
the difference? Isn't one just you flip the time from one to the other?
Well, yes, but the time, the direction of the time is important for me.
Ah, okay.
Yeah, I mean, topologically, we have a similar effect, but the direction of the time is important. Yeah, it's true. Yeah. So, but yeah, I mean, if I see what happens as time passes, you know, when I see one type singularity, I have more holes, right? So if I do, I mean, one way to prove it is it's possible to change the metric so that all the 1 type appear before all the 2 type, right? And then you see the 1 type introduces a number of holes, and then the 2 type start closing up the holes. And you can see, well, of course, some of them, I mean, when you introduce a hole, there are 2 possibilities. You can close it by type 2, or you can also add a cap and close. So when we do this, that's one reason actually that 1 are not very useful, while 2 are more useful, is that 2 are somehow topologically non-trivial always, while 1, you might think something happened, but maybe this thing that branched off is capped off by a disk later, so nothing happened. While for 2, always something happens. Every time you do a move, you do a 2, since you start from X, you are going to get a closed geodesic like that. Okay? So, and this is what I'm going to use to construct the graph. Okay, and again, this is what I'm going to use from this discussion, that N2 is equal to G. Okay, so now let's see how I'm going to slice my surface. I only care about the type 2 critical values, and I may assume by just slightly changing the metric that this EI minus TJ doesn't lie in Z. Okay, so this is just for technical reasons. It's just more convenient for me not to have critical points where I slice. Okay, and now I'm going to take these slices. I will start from T1. Okay, so the first one minus 1. I don't know what happens in the first one. Maybe it's something like that. So maybe this is T1. I will start from T1 minus 1. And then I'll take slices of length 1. Actually, sorry, I think actually I might need to take all critical values and slice, but anyway. So, okay. And then, of course, I'm going to stop after the last one. So maybe my surface goes on there, but after the last, I'm just going to stop. After the last time I meet this, I'm stopping the slice. Okay, I only consider this slice. This I don't care about. And of course, one reason I don't care about is because you can shorten the area, nothing happens there, right? So, and now for each generic level, so by Sard's theorem, we saw that most of the time we have simply closed curves. So I'm going to denote by LT the union of non-contractible simply closed curves in F inverse of T. So what I'm doing here is, so I have my surface, and now the surface can have things like that. Sorry. So the point is, I look at the level and okay, maybe further. So this is good, right? So in this example, I have only one, and these are not good. These I ignore because they are contractible, right? So I only care when I'm going to define my graphs. I only care about the non-contractible curves in a level set. Okay, and now how do I make my arc, my graph? Maybe I will explain this and stop there. So I'm at a level, so I have my point P, take the distance function, and I'm at a level and I have some nice simple closed curves at a given level, and this is the slice where this lives on. Okay, but then in order to create my graph, I'm going to add something to this. So this is not a very interesting graph, right? It's just a union of simple closed curves, and I wanted something more interesting. I'm going to go to the next level, and I'm going to look at the handles, at the type 2 critical points that I have there. Maybe there is none, then I'll do nothing. And I'm going to take the geodesic going from here to this point and back. Okay, so here and back. And of course, all these geodesics are distinct, right? Because there is unique geodesic and so on from this. Maybe it goes like that. Maybe it goes like that. Okay. And I'm going to add to my graph all these arcs. Okay. So this is going to be my graph. So this is the idea. So I wanted to get. So again, if my surface were thin and long, immediately the co-area inequality is going to give me. So that my surface is quite compressed, right? So I look at the level sets. The level sets are not very interesting as graphs because they're just union of simple closed curves. Somehow I need something that will help me encode the complexity. And the complexity is very large, it's G, right? So this G can think is very big, right? It's huge. And the surface is compressed. So since the surface is kind of short, if I look at the level sets, it's likely I'm going to get many of these arcs, so I'm going to get graphs of high complexity there. That's the idea. Okay, and then I'm going to use both the co-area inequality and this. So I'm going to use the co-area inequality now only for this part, for the green part. I will use the co-area inequality for the green part to get the inequality I want, and I will use the red arcs to show, because I know that in total I have G red arcs, right, all over, to show that some of these graphs has high complexity. So I need two inequalities for these graphs. I need an inequality saying that they're not very long, right? And now, why they're not very long? Well, they're not very long by the co-area inequality and by the fact that these red arcs are not at the same level, but they're not far apart, right? So all these red arcs have length 2, right? Okay, at most 2. Have length at most 2. So we don't increase the length of the graph by much. Okay, but they increase the complexity by a lot. So yeah, and then there are these, of course there will be some inequalities, right? But that's the philosophy of this proof. Bound the length by the co-area function and show that the complexity is big because you have a lot of these red arcs. Okay? And I'm going to So yeah, it's not in the middle.
Can you still say a second? So you take an arbitrary level, you see the green
Right.
circles, and then those points were the type 2
I
critical
look-
points in the next.
I look only at the next level. Of course, they appear in other levels, but I'm going to construct many graphs. I'm not going to construct one graph. I'm going to construct a graph at every level, and I hope that one of these graphs will do the trick, right? Not all of the graphs will do the trick, okay? So, I mean, for example, it's possible. There is no contradiction at one level to have a huge arc, and then at the next level have no red arcs. So this level is useless, right? But I don't care. There will be some good level. That's the point. That's the philosophy. There has to be, because if you write down the inequalities, you see there has to be a good level, right? And that's what will be next time. Okay. Sorry, I'm in the middle of this, but
That's good.